So in order for us to talk about weak acids, Ka and pH, we're going to work our way through a couple of calculations so that we can sort of make general comments about them and learn how to basically do them. We're going to learn a couple of styles of question, and we're going to learn one thing that some of you are not going to like at all. And but if you try it a few times, you might find out that it's not so bad. So what are we going to need to know? Well, we need to know that for weak acids, we have an equilibrium. And the equilibrium expression is going to be, because water is a liquid, it can stay out. So our equilibrium expression is going to look like that. And that pH is the negative log of the hydronium ion concentration, which you see up on the top of the equilibrium expression. And if I need to find the concentration of hydronium, and I know the pH, then I do the inverse of the log operation, which is 10 to the exponent negative pH. So all those things are going to be important. We're also going to use ice tables. Now, at some point, we'll modify our ice table a little bit, but we're going to be using ice tables. Okay, there's two ways I can do things. I can have a question like this, where I give you a concentration of solution, and I give you the pH, and I ask you to figure out the equilibrium constant. That makes sense. What's the equilibrium state all about? So for this one, we're going to use HPro as our acid, and then you can see how it dissociates and so on. So I'm going to set up my ice table the way I set up ice tables: the initial concentration, how that concentration is going to change, and what the equilibrium concentration is going to be. And you'll notice that the water, because water is a liquid, its concentration is not changing. Total amount maybe, but not the concentration. Okay, so now I take my equilibrium piece of the expression and I keep going. The other piece I was told in the question was that at equilibrium the pH was 2.78. So if I think about my ice table, one of my blocks was a concentration of hydronium. So I can use the pH calculations to figure out what my X is. There, X is that concentration. And if you recall the ice table, or maybe if you wrote it down, that would be a good idea. Then you'll notice that X was also the concentration of the propionate anion after, or in what's called the conjugate base, after it's donated the proton. And then the amount of acid still remaining was the amount that I started with minus the amount that dissociated. So I can use the ice table again to figure out the concentration of undissociated acid. Put all of those values into my equilibrium expression, and I end up with a K value of 5.7 times 10 to the exponent negative 5. Okay, just to summarize that. So here's the original question, here's the ice table set up, here is the equilibrium expression to find the equilibrium law, I guess, and then I go through some calculations to find out what my pH is, what that means for X, what that means for the other X, what that means for the 0.05 minus X. Put those into the equilibrium law, calculate out the K value. So the question ends up looking like that, start to finish. Okay, other option is if I know the K value, and to be very honest with you, there are tables full of K values for weak acids and weak bases, so it's likely we're going to know the K value. What I won't know, and what I'm going to try and predict or calculate, is if I have this concentration, what would I expect the pH to be? So this kind of question. So a typical wording would be something like that, where you're given a concentration, you're given an acid, not that the acid necessarily matters, and you're given a K value. You might have to look it up in a table, but you'll be given a K value. And it's always good to have a reaction, at least one that, even if it's not the proper chemical reaction, so I've used AC to be acetic acid, and I can see how the equilibrium happens. Set up my ice table. The difference is I don't have any information to find X's from the original question. So that's what I'm going to be using, or that's what I'm going to be doing rather, is I'm going to be using the other information to find X. So before, X was in the middle, now X is going to be at the end. Equilibrium law, and at this point I don't know any of the values that go anywhere, but I do know what they're all going to equal to. So I'm going to substitute and solve for X. So put the things in as I know them, and then I'm going to solve for x. Now, here's where we have our options. That's the part where I said some people won't like it. If I simplify my expression a little bit, I get to here. And at that point, I've got two options. Option number one is to do some rearranging and some math and do the quadratic formula. And some people like that. And some people have the quadratic formula programmed into their calculator already, and that's okay. The other option is something called method of successive approximations. And it's something that looks weird at first, but it's actually really easy to do. It comes from a time where we didn't have easy to use graphing calculators or fancy calculators at all. And so doing something like a quadratic was a real big lot of pencil paper work. Okay, so let's say you decide to go quadratic formula. There, of course, it is. You're going to do some rearranging. You're going to multiply things through. You're going to move everything to one side to set it up so that it's ax squared plus bx plus c equals 0. Set it up in that standard form. Dump it into the quadratic formula, where in this case a is equal to 1, b is equal to 1.8 times 10 to the exponent negative 5, c is equal to negative 1.8 times 10 to the exponent negative 6, and push all the buttons you need to push. Successive approximations. If you don't have a fancy calculator, this works. If you don't have any calculator at all, this would still work, but it'd be really hard to do. We're going to start with the equilibrium law again. We're going to partially solve it just a little bit. At this point, though, I'm not going to multiply things through, and I'm not going to move everything to one side. What I'm going to do is I'm going to try and solve for that x over on the left-hand side. Now, obviously, I cannot do the square root of all of that as it stands. So what I'm going to do is I'm going to scratch my head a little bit, and I'm going to say that as a weak acid, the amount that dissociates is pretty small. So when I subtract the amount that dissociates from the amount that was originally there, it's going to end up being rounded off to the same thing. In other words, that first x, I can ignore it. I'm going to assume it's pretty small. Then my expression changes to something where I can easily take the square root, so I do. I take the square root, and I get 1.342 times 10 to the exponent negative 3. I'm not done yet. I'm going to assume that, okay, that's not quite 0. It's small, but it's not quite 0. So I'm going to assume that, all right, instead of x being so small I can ignore it, let's say that x is that. So I put it back into my earlier expression, and I use it. And I use that to find my second value of x. And when I do that, I get a different number. Not crazy different. 1.333 times 10 to the exponent negative 3. So it's only different by a little bit. And if you like rounding off, you'd say close enough. But I like to make sure. So what I'm going to do is I'm going to assume, okay, maybe this is x. I'm going to put that back into the expression. So just taking what I had before, moving it to the top here, I'm going to assume that x is this number. Put it back in. Do the math. Come up with x3. Now the nice thing is, x3 is about the same as x2. Now I've only got 3 decimal places. If you took it out to 4 or 5 or 6, maybe you'd find out that somewhere down the line it is a bit different. But we don't care. It's holding pretty steady. Which means, remember that old left side, right side check thing you did in like grade 9 or grade 10 math? We've kind of done it. We've confirmed that when I put that number in, I get that number out. So I'm done. Now, x here, don't forget, x was the concentration of hydronium ion. So that's what I'm looking for, because remember, I'm after pH. And for pH, I need concentration of hydronium ion. So I put that in for the hydronium ion for the pH calculation. I end up with a pH of 2.785. Yes, I could do some rounding off there. Okay, back to the beginning just to show you what the question would look like start to finish in not so slow time. Because I've got a lot of detail that you don't really need to write. You don't need to say assume that x, 2 is equal to. So here's what I do kind of expect. You'd have a reaction. You would have the equilibrium system. You would have the ice table. Now I've modified the ice table. Instead of initial, change, and equilibrium, it's now initial concentrations, final concentrations. At this point, our changes are pretty standardized, and we can probably skip that middle step. So we're going from start to finish skipping the change part. So initial and final. You want to have your equilibrium law. You want to have that set equal to what the k value is that you got either from the question or from the tables. You want to start to partially solve it. You want to set up the, whatever you want to call it, the expression here if you're going to do successive approximations. And then I usually just write down x1, x2, x3, end of story. I don't do a lot of explaining. I don't do a lot of, arrows pointing to where that's going to go in, because successive approximations is one of those things that pretty much everybody knows what's going on. So as soon as you start doing this, everybody knows, oh, successive approximations. Okay. Now, did I hit not? Oh yes, I did have I don't have the pH calculation there, but I do have that you turn that into pH. Make sure you turn it into pH, because that's the question. Okay, now we should be able to do both those styles of questions, both concentration and pH telling the K value, or concentration, K value, predict the pH. And we'll be able to do that for any weak acid and any weak base. One final comment about successive approximations and how many loops or rounds or cycles you have to go through. It kind of depends. The smaller the value of K means that the less dissociated that acid is, which means your first thing where, well, let's assume I can ignore it, makes that much more valid. So if you have a really, really, really weak acid, twice through would be enough. Once through would be enough, but twice just to confirm. If you've got a moderately weak acid, you might have to go through. The most I've ever done is about 5 or 6, and at that point I was really wishing I'd done the quadratic formula, but at that point I'm almost there. Anyhow, we generally work with fairly weak acids, but these are the things that we should be able to do with them, and then we'll get a whole lot of practice doing them.